Once again, thanks for joining
Yeah,
us today. We really
you're welcome.
appreciate it.
That's a pleasure. Yeah, so I'm going to talk about SDR, software-defined radio, and applications for amateur radio. And the idea here is to focus on how does it work. It's a very wide topic, and it's not easy to present this in half an hour, or in even 1 hour, or even 2 hours. It's a very large topic. So please, those of you who are already experts in this, I will have to take some shortcuts, otherwise it's gonna be difficult. So let me start. Just make sure that yeah. So basically, this is the outline I will propose. I will introduce the SDR system, and in fact, I will try to explain how it works, and you will see that the way the hardware is designed and the way is, of course, tightly connected to the way the software works. And these two things cannot be disconnected. So I have to explain the background. I have to explain how the receivers do work. And then I will spend some time on the software. But you will see that at the end, that's quite logical, in fact. That's there are some theoretical topics that might be difficult, and I'll try to make them as simple as possible. So once again, please, sorry if you believe that I'm taking too many shortcuts. So first of all, is this something new? Not, of course not. This was presented in 1991 by a guy in his PhD, in a PhD thesis manuscript, Joseph Mitola. It was in 1991, and he presented this as something as a plan for the future. He said, well, considering the increase of power that is available in the computers, that makes sense to be able to do the processing in real time. And that was in 1991. And of course, at that time, the computers were not as fast and as efficient as they are today. So when you look at your handphones, if you compare the power of your handphone to a PC or even the ZX81 we had 30 or 40 years ago, there's a there has been a huge step forward. So of course now we have the power, the processing power, to be able to do the computation in real time. And that was not possible a long time ago. But the concept and the key techniques are not new. What is new is the fact that your home computer or your Raspberry Pi has enough power to do it. And that's the key thing. So I'm going to now explain a bit more how it works inside. So first, let's start by something that I hope you all know by heart. That's a simple heterodyne receiver block. Basically, you see that you have, let's say, three main things: filter in the input, a mixer that is converting the signal of interest to a intermediate frequency, and then a demodulator. Okay, basically the electronic circuit at demodulation is specific to the modulation mode you're listening to. If you're listening to AM, FM, or SSB, you would have a different circuit. And but the first part, the RF filtering, amplifier, and mixer are usually, let's say, common and are not really dependent on the modulation you're listening to. In an SDR system, basically, of course, you start with the same signal, so you need an antenna at least. Software antenna does not work yet, or it's not yet so efficient, let's say. You need a RF amplifier, and the key difference is that you sample, and I'll come back to this in a minute, you sample the signal, so that is to say that you will take some data measurements of this signal, and then the right-hand side is now not a circuit, but an application. You remember that joke about the iPhone? You need a coffee machine, just download the application. That's roughly the same. You want to decode an amateur modulation, just download the code. You want to have your PC as an ADSB receiver, download the code. You want to receive and decode weather maps from satellites, download the code. That's the same. So basically, the RF on the left side is here to convert the data in a format that can be processed by the applications you have on the right. That's the idea. Of course, that looks simple. But it is simple, but there are some tricks, and that's what I'm going to focus on now. So that's the key signal processing concepts. and as I said several times, with shortcuts, of course. So basically, just to introduce these shortcuts and these techniques, I would like first to take a few seconds to look at these different instruments that you may be familiar with. You know the oscilloscope, you know the spectrum analyzer, and you know the power meter. Basically, these three elements, the three instruments, are plotting the same data, but in a different way. The time domain, so what I'm going to introduce here is the key difference between time domain and frequency domain. And you will see why just in a minute. Basically, the spectrum analyzer is plotting something in the frequency domain. What you see is a frequency and an intensity, while the oscilloscope is plotting an intensity and amplitude over time. Okay, so we are on time domain or in frequency domain. And in fact, the power meter is also plotting an information in the time domain, but at a different speed, let's say. That's average. So basically, you take the same information from your circuit, from the probe, and what only changes is how you represent the same information. But on the circuit, you have a probe, and this extracts, I would say, or this takes a sample of RF signal. And that's just a problem of presentation. That's just a problem of the way you use or the math transforms you use to represent the data. So the key thing I said is to transform these RF signals to numbers, and that's, sorry, I just need to move my face I see on the screen, that's not very useful. So this is done by the analog to digital converter. This is, you can see this as a voltmeter, but instead of plotting the, instead of using your eyes to read the value, this just notes the value on a table. So that's basically what the sampling system is doing. It's taking values, like a voltmeter, and reporting the values it has seen, okay? And this is doing this at a certain clock rate, okay? So you can see here in yellow below the circuits. So the ADC receives a clock, and that clock tells him when the measurement has to be done. And it outputs a value, which is a digital value, and the accuracy or the precision, I will not spend too much time on this right now, is a function of the number of bits that is proposed by the ADC. It's like if on your voltmeter, the number of the scale precision, let's say, the number of dashes you would see on the voltmeter. So basically, you see from your eyes that the bigger the number of bits is, the more accurate the curve looks like, and that's why more bits you have, better it is. To make it simple, just the note on the back of the slide you can see is that there are some receivers give a certain number of bits, but we have to be careful. The useful ones are the effective number of bits. I think I will come back to this later, because when you're doing measurements at a very high speed, there can be uncertainties or errors that leads to false measurements. But I will not spend too much time on this one. Then the problem that comes is how often this clock should work. I said that I have to make measurements at a certain speed, and in fact, the key thing is that the measurement speed is directly related to what you want to measure. I have not the time to spend too much on this, but the idea is that there is a rule, and that's the Nyquist-Shannon theorem. Sorry for this. It says that if you sample at a certain speed, which is frequency, Fs, the sampling frequency, then the maximum bandwidth you can see is the half of it. And this is very important because if there is a signal that is not respecting this criteria, then you will see something strange, which is called aliasing. Maybe you know that those of us who have white hairs, you may remember these films when you see cars and you see that the car is driving, and you see the tire that is going counterclockwise, going backwards. That's typically a problem of aliasing. The pictures are taken at a certain rate, and if the car goes too fast or not fast enough, then it looks like the rotating the way it rotates is not logical. So just to summarize this very quickly, there is two very important things in signal processing: one time domain representation and one frequency domain representation. And in fact, one man, Joseph Fourier, invented a magic formula, and I will come back to this, called the Fourier transform that makes you go from one to another. It's just so from the time domain, you apply the Fourier transform and you go to the frequency domain. And if you want to get back into the time domain, it's the inverse Fourier transform. So basically, a spectrum analyzer or an oscilloscope are exactly the same. Just one is applying a Fourier transform to display the frequency domain. I mean, the digital ones, of course. So just to explain a bit more how it works. The idea is the following. You know the harmonics, I mean, fundamental frequency and multiples. And in fact, you can see that depending on how you combine these different signals, how you combine these harmonics, you will be able to generate, to synthesize different types of signals. So you see that in the figures that you can have square ones or sawtooth signals, and the only difference is the way you combine these harmonics. So basically, what I'm saying here is that from a description of the frequency domain, you can go to the time domain. So, to take examples, depending on what are the harmonics you select, fundamental and others, and the amplitude you use, you will be able to generate from the same set of signals, you will be able to generate different shapes in the time domain. Okay, so that's the key thing with the Fourier transform. You can see this as a recipe. You're making a cake, and the Fourier transform is able to generate the cake based on the ingredients. And of course, what's interesting is to do this the other way around. When you want, looking at the cake, know the recipe. So the Fourier transform is able to do this for you. It looks at the cake and say, there is that amount of salt, that amount of flour, and so on. So basically, the Fourier transform is the key tool in everything. It's just able to go from one signal to its fundamental elements that were used to make it, or the other way around, from the fundamental elements, generates the time domain signal. And you will see that, in fact, at the end, this is what is used in most of our amateur radio equipments, this simple Fourier transform formula. So that's what I show here. From a set of value that has been measured from the analog to digital converter, you see value 1, 2, 3, 4, 5, and so on. When you apply the Fourier transform, you will get the same number of values, but they don't represent the same thing. In the time domain, one value is a measurement at a certain time. That's the voltmeter we saw in the beginning. So value 1 is the first value you could read on the voltmeter, value 2 is the second, and so on. And if you use the Fourier transform, what you have at the output is the amplitude of a certain frequency and the phase of this frequency. So you have the same number of values, but the first one is in the time domain and the other one is in the frequency domain. And you can, of course, go back by using the inverse Fourier transform when you transform this amplitude and phase into time domain values. Sorry for this, but you will see that's useful. So now you've seen that we are able to go from one way to another by just applying that magic formula. But there is a small problem we need to consider. A small problem. So I'll try to explain this here. You see this yellow dot, and assume that this yellow dot is rotating. In fact, my slide is wrong. It's counterclockwise. Okay, it's turning on the left, and we want to plot the yellow line here, which yellow line is in fact the cosine of the alpha angle, of the theta angle here. So that plots something like this. You recognize something that looks like a sine or a cosine plot, of course. So if you look at this, so you each time the yellow point is going forward, we plot the value of the horizontal yellow line, and we have this nice cost plot. Okay. Now we repeat the same experiment, but we go the other way around. We turn clockwise now. Sorry for the mess on the slide. And the problem we have here is that we have the same plot in the end, because this plot is in fact wrong. There is one information that is missing. The information that is missing is in which way we are going. That is to say, if you assume that here we're on the first point, on the first plot, we're going 1 turn per frequency, 1 hertz, okay, on one certain sense, on one certain way. The other one is a negative frequency, let's say, if we assume that clockwise is positive and counterclockwise is negative. Basically, I'm saying that the positive or negative frequency lead to exactly the same plots. So we have a problem. We've lost the sign of this transform. So what is the problem? Well, if we now look at the Fourier transform, we have the same time domain plot. So how do we represent positive or negative frequency? And in fact, excuse me, in fact, what you see is that you have, if you use the Fourier transform, you have 2 peaks, okay? And that's somehow exactly the same when you mix, you take a mixer and you have the local oscillator, the RF signal, and you have 2 outputs, frequency A plus frequency B and frequency A minus frequency B, for example. You have 2 combinations, 2 solutions. So the problem here is that if we use this to plot our spectrum on our SDR software, we will have a symmetry, which is not good. Excuse me. And just a side note, of course, if what I'm sampling is HF signal, I know that there's only positive spectrum, so I just don't care. But in our case, if we're sampling HF or VHF band, we wouldn't like to see these 2 things. So in fact, we have introduced something which is, I call this a complex fix. The idea is that, in fact, we will sample the signal in such a way that we know in which way it's going, if it's going clockwise or counterclockwise. And to do this, we will use, in fact, you will see in the next slide, we will use 2 ADCs. And the thing here is that you may have heard these magic tricks or these words saying, oh, I'm doing IQ sampling, I want the IQ signals and so on. What is this? In fact, that's just to say that we use complex numbers. And in fact, when we do a measurement, we take 2 values, okay? And so we have the in-phase value, which is the I, and we have the Q, which is the quadrature, or the I and the Q values. Sorry, I'm thirsty, so that's why my throat is not good. So I and Q means that you have complex numbers in terms of what we call them in mathematics. So we have 2 values. And the good thing is that if you sample in complex numbers, instead of you use 2 ADCs instead of 1, then you double somehow your sampling rate. You will see this. I will come back to this. I know that's tricky, so I don't want to spend too much here. Otherwise, we'll get lost. So basically, here is the receiver, how it works. You have on the left the power amplifier, and instead of having 1 ADC that takes 1 sample at each clock, you take 2 samples, and the second ADC is just there is just a 90 degrees phase shifter between the 2. Okay, so you take the in phase, that's the E, the I channel, and you take a shifted signal, that's the quadrature signal, the Q channel. So now you have I and Q, and that's nice because now we have the spectrum that is on the good way. So it means that you see that the hardware and the hardware is in fact directly impacted by the way we process the signal. And I'll take some examples here. The first point is that what happens if our ADC, so this stuff here, okay, sorry, I could just go back. Our ADCs here we use to sample the signals. What happens if the signal is too strong in the time domain? You see, well, the yellow curve is truncated. We are missing the top of it. Excuse me. So when we sample the signal, we see that if there is a saturation, the time domain plot, we have something missing. So in the frequency domain, we will see that we have a lot of strange ghost signals appearing everywhere. So typically when you use your SDR at home and you see that you have a lot of strange signals appearing everywhere, reduce the gain. It's because you have saturation, typically. That's just a consequence of the Fourier transform, in fact. Something also very important is the dynamic range. I mentioned the number of bits, and the thing is, I said that you need a lot of them. Just let's explain why. Let's say, for example, that you have in 40 meters band or 20 meters band a very, very, very strong local station that is 59 plus plus plus, and you want to listen the DX station, which is very weak. The problem is that while on the spectrum, they are separated in. You see the difference here. They look nice, and you say, that's not a problem. But consider that the EDC needs to take the two signals, and you see here in the time domain that, in fact, it's very, very difficult to see the contribution of the DX station, which is the signal is in fact polluted, I would say, somehow in majority by the local very strong station. So one thing you should remember is that if you have a 1 bit in your ADC, your dynamic range is 6 bits. So just to explain what it means, if you buy a RTL SDR, the cheap ones, the USB dongles, which are claimed to be 7 to 8 bits, it's 50 dB max of dynamic range. So you see that in HF, it's a bit too short in case you have a broadcast station and a DX very close to it. Another very important thing is the clock quality. So what do I mean here? Is that I said that the samples must be taken at a constant rate and as that is the sampling rate. And in case your clock that generates the tops is not accurate enough or is drifting, for example, I will show you here what is the consequences of this. So you see the yellow line here is the difference, I would say, between the earliest and the latest rising edge of this clock. And that's just the distribution of this. So you see that they look exactly the same. The key difference is the scale. You see on the back, it's roughly 0.02, while it's roughly 0.01. The magnitude of 10, sorry. So if you look at if you look at this here, what the results on the time domain, on the frequency domain, you still see your signal, but the difference is the noise floor. You see here, it was the signal to noise, sorry, was roughly 85 dB, while the noise signal to noise is roughly 73 dB. So we have somehow lost more than 10 dBs just because the clock is not good. So that's very critical when you have equipments that you take care of the very stable local oscillator and very stable clocks for sampling. Sorry, just a second. I'm back. So just somehow to summarize quickly about the equipments. What is the key point when you want to buy an equipment? Well, first of all, you need to know what you want. The universal system that works from 0 to 10 gigahertz does not exist. Sorry for this. You need to know what you really need, and I'll try to elaborate a bit more here. If you're working in HF, you will face in the bands very, very, very strong signals. Broadcast stations that can be very strong, while most of us are looking for weak signals or DX, where the signals are not that strong. So you need something that is able to digitize the two at the same time. That is to say, the very strong signal and at the same time the very weak one. Okay. So HF is a very, very hard case where the dynamic range is really critical. If you're listening to VHF signals, it's, well, unless you have FM broadcast very close to you, but most of the time I would say in 2 meters bands or well, in VHF there are 6 meters, there's not so many strong stations out of our bands. In UHF you need to be careful because it depends on what you have close to it. You could have DMR or other transmitters close to you that would be very strong, and then it's quite similar to UHF. And above that, honestly, would be very happy to have the crowded bands, but that's not the case. So basically, I would say something that has a good sensitivity is good enough. So you see that depending on what you want to do, depending on what you need, the price of the investment is the price to pay might be different. One critical thing when you use these HF systems, these SDR systems in HF, is to filter a lot. If you can have a pre-filtering, that would improve a lot because that would somehow reduce the unwanted strong signals that could be digitized by your and could enter your ADC and put him in a very bad position where he has to decide if he keeps only the very strong broadcast station or the one you are looking for. So first of all, really key question is the dynamic range you really need. It, as I said, it depends on the frequency. Look at the number of bits. The more you have, the better it is, of course. And the frequency stability. I showed that in some, well, if you're listening to SSB at very high frequencies and the clock is not stable, it will be difficult to hear this. Okay, so that's the hardware side. So now we have samples and we have IQ, complex samples that are going out of our USB cable, and we need to process them to have a nice waterfall on the screen and be able to listen to the signals. So now let's go to the second part and explain a bit how that works on the software side. So basically, here's a screenshot that you might recognize. It's the SDR Shop software, a very famous one. I think that's the one that is the most widely used. And that's why I've selected this one. So basically, you have, I would say, 4 key elements on the screen. You have, of course, the VFO on the top, where you select the frequency you want to listen to or you want to decode, and that applies to the very small center line that calls the demodulator applied here, this range here. That's the center of the display. Below, you have the waterfall, and on the left, you have settings, and here at the moment, the one that is displayed is the demodulation. So I've selected LSB, and I'm working on HF on 7.104 megahertz. So you've seen that the signals that the software is receiving is a series of values, a series of voltage measurements taken at a constant rate, and that's just what the software is receiving, nothing more. So that's the first thing, which is quite obvious now, is that this is time domain. That is to say, the USB cable is carrying time domain samples, arriving one after one. And to plot the FFT, the spectrum display, that's just a Fourier transform. We take a bunch of signals, a bunch of consecutive values from the stream, apply the Fourier transform and plot. That's pretty simple and straightforward. Nothing special here. That's exactly the time to frequency domain transform. The waterfall now. In fact, it's just the same. That's just the same. Instead of doing one single plot, we repeat this process several times. So you see the purple boxes. So we take one first series of samples, apply the Fourier transform. So what you have here is just a spectrum. The same, exactly the same than this one. The key difference is that you will somehow assign colors depending on the height of the mountain. If it's the flat land or a strong signal with a high mountain, the color will be different. So you have a color map, and depending on the intensity of the height of the mountain, we will select a different color. If it's very strong, the signal is very strong, then it's red, for example, in this one. And if the signal is weak or small, we'll use, for example, a yellow signal. And that will decide which is the color of the pixel you see on the right. So basically, the orange horizontal line is the process line, the current line I'm painting. So I take a series of value, do the Fourier transform. So that gives me a value per frequency. And then for each value per frequency, depending on the intensity of my color table, I select the color of the pixel. And I repeat this continuously. And that's why the line is, the image is scrolling down, basically because I'm painting and painting and painting and painting. So the process is in fact quite simple, but this is consuming quite a lot of power in your computer. So now you've seen that in fact the waterfall and the spectrums, if you go back to this slide, the two things that we're all fan of because it's very interesting. You can see if you have a station close to you, you can see what is the, if you're used to use this application, you can recognize the modulation with your eyes. You have the it's not artificial intelligence, it's the OM brain that recognizes the signal and is able to say, this is USB, this is LSB, CW, and so on. Your brain is very efficient for this. And in fact, that's just using Fourier transform frequently and very fast and painting the signals. But that's pretty simple, in fact. What is a bit more difficult now is the demodulation. Basically, you see that from the yellow time domain plot above, that's what is coming out from the USB or other connection, but from your external hardware. You receive a series of numbers, and these numbers are, as I said, the measurements provided by the ADC, the analog to digital converter, but this samples over a wide band. I mean, the full band that is seen by the receiver, the IF band. So you need to extract the portion of signal, the area you want to decode. That's exactly what you do in the Heterodyne receiver. You have a local oscillator and a mixer. We do exactly the same here. We select the band of interest by generating a fake or a digital BFO, just by using a sine and cosine signal, and we just make a multiplication, so that's exactly the same that I was doing in a real one, and then we do a filter, bandpass filter. And the key thing is with SDR is that the shape of the filter can be generated on demand. You remember those receivers when you had to buy a CW crystal filter? It's very expensive, and depending on the bandwidth you want, usually our rigs could afford 1 or 2 different crystal filters, but not more. The good thing with SDR is that the filter is just a series of values. It's just computed by the computer. So you want 100 Hertz, we generate the shape of the filter for 100. You want a USB filter, which is 3 kilohertz wide, no problem. I just generate the values. So that's the key difference. So in this example, I was able to generate, in this simulation, I generated a filter that is something like 80 dB, that is very straight, very sharp, and has a bandwidth of 2 kilohertz. And that was just, I applied the magic formula to generate the values, and that's it. And I got my value. And so the key benefit here is that we can generate the shapes we want, the bandwidth we want, without having to open the rig and change the crystal. That's quite useful. Okay, so now we have this post-filter values, so we now have to demodulate. And so it means that we have extracted the signal of interest, let's say the QSO we were listening to. We have filtered, so we now have I and Q signals, complex signals, just in the band of interest. Now we need to do the demodulation. And in fact, that's the most simple part, to be honest. And I'll take a very simple example here. Sorry, I will have to ask you to go back to your minds to when we were young and in school. Probably some of you, sorry for this, do remember the Pythagoras theorem, which says that the length of A is of A squared is the sum of I squared and Q squared. This length here is the sum, this squared length is the sum of this one squared and this one squared. Sorry for my English. So basically, if we assume that I and Q are the 2 values we received from the previous stage, computational stage, and we can then compute A as the amplitude, which is square root of I square plus Q square. That's the only last formulas I would show this morning, no worries. And we can estimate the angle, phi here, by being the inverse tangent function of Q over I, okay? These 2 formulas give you the amplitude, the length of A, and the value of the angle here, okay, of the phase. So why this? Well, basically because amplitude demodulation is just computing A. We have I and Q, we say the amplitude is the square root of I square plus Q square. That's it, and I push this to the loudspeaker. That's done, finished. I have my AM demoed. Want to listen to FM? There's another step. First, I compute the phase. So I estimate the inverse tangents of Q over I, and then do this several times and make the difference between 2. And I have my phase difference. That is the FM modulation. So what I'm trying to say here is that whatever the formula is, the process is always the same. The input is a series of values coming from our stages, we just apply one formula. This one for AM, this one for FM, and of course other ones for SSB, and so on. And then we just push the output to the loudspeaker, and that's it. That's done. That's pretty simple, in fact. Sorry, before the conclusion. So if I go back to this, it means that the demodulation stage is just taking the values, getting out the filter, and doing sums, square roots, and that's it. So if I go back to this, when you select on the right on the demodulation stage, NBFM, AM, LSB, USB, and so on, in fact, you select in the computer software which formula you have to use, and that's it. I hope you see that you saw that it's not that difficult. So, as a conclusion, you see that as long as you have the good software and you know the formula, you can demodulate this. And this goes back to the previous talk about some modulations. If you know the formula, then you can demodulate. If it's not the case, then you have to reverse engineer, and that's another story. So that's the message behind this is SDR is always possible when the specifications are public. Otherwise, it's another story. The processing power can be provided by the computer. What it means is that some demodulations need a huge amount of power, computing power, and sometimes Raspberry Pi are just, or small simple computers are not even today powerful enough to be able to do the decoding in real time. So be careful. Sometimes some modulations need a huge computer, in particular if you want to have those very nice waterfall on wide screens with high resolution and so on, then the computer will cost you much more than the SDR. And of course, make sure that the RF signal is properly sampled, because you can have the best formula in the world. If the ADC doesn't work, there's no magic. You cannot transform a badly sampled signal to something that looks nice to your ears. I think that's all. I hope that you're not all sleeping. Thank you very much.